Good day, everyone. Welcome to the ninth lecture on electrodynamics. And here, our reference is again Introduction to Electrodynamics by David J. Griffiths. And this book is highly recommended for you. And I hope you would be able to get a hold of a copy of this book in the future. So, for this particular lecture, we will be starting with the curl of the electric field, and again, for a point charge at the origin, the electric field is given by this equation here. So the electric field is just 1 over 4 pi epsilon sub O Q, which is the charge, and over R square. That R there is the distance from the origin to the point where the field is measured. So you have R squared of that. And the R hat, this one, is just the unit vector pointing to the direction of the electric field. I mean, in that case, you have a radial direction of the electric field. That means the electric field starts out from the center and it spreads out in all directions radially outward if the charge is positive. Now we calculate the line integral of this field in spherical coordinates from point A to point B. So of course, point A, if they are different, then point A would have a distance RA from the center, and point B would be a distance RB from the center. They may be equal, but of course we must assume that here that they are not. So the line integral of the electric field is just equal to the integral of the electric field dot dl. In spherical coordinate system, dl will just be dr r hat plus rd theta hat plus r sine theta d phi hat. In this case, your electric field is only in the direction r hat, so this term will not be of use in the integral because they will be dotted to component that has magnitude of 0. So our E.dl will be 1 over 4 pi epsilon q over r squared dr. So if we integrate that, we will have by the way, let's go back to the figure. So if A would be in this point and B is here, then you are doing the line integral going from A to B. Your path could be a straight line, or your path could be any curved path joining the points A and B. So of course here, as you can see, RA is different from RB. So if you integrate that, you have this one here. So if you have a point charge, you can take the q out of the integral and just integrate dr over r square, which gives you 1 over r, the integral, and then you will have you will have to evaluate it from RA to RB, since your path goes from RA to RB. So now, if you go from one point to another point where the distance is different, you will have a value of the integral of E dot dl. But when you go from a point, take a path going to the same point, this means to say that your initial and final point are the same. That means that you are in the same distance as initially you're in the same distance as your final distance from the origin. So in that case, your RA is equal to RB. So that would be 0 if you do the closed integral, because your final point is different. It's the same it's the same with the initial point. And also, you can also say that if you go from another point to another point with the same distance as the origin, with the same distance from the origin, then you also have the integral of the line integral of the electric field would also be 0, since they're the same. Their distance from the origin is the same. So in that case, if you're on a surface of a sphere and you are always, if you're measuring that on the surface of a sphere, you're always on the same distance from the origin. So if the origin is at the center of the sphere, so that would be that would give you the line integral of electric field would be always 0 on the surface if the origin is at the center. But there is a case also when you have a conductor, you'll always measure the potential at or should I say also the line integral of electric field with respect to the line integral of electric field also the same at any surface of a conductor. So later on you will know why is that. And we note that the Stokes theorem. So this is just equal to the integral of the curl of E dot dA. So that you can say this one here. I apologize for the sound of the rooster. So anyway, continuing, we have now we only showed this result, these ones, when we set the origin to be at the center of the sphere, but the result holds wherever the charge is located. So now if there are many charges, so each of these charges will give off electric field, E1, E2, and so on. So if you take the curl of the sum of this electric field, then you're also taking the curl of each of the electric field, and that is also equal to 0. So we can now define the electric potential. So the curl of the electric field is always 0. This is a special property of the electric field which reduces our problem into a scalar problem, because like we are engaged to a vector problem, we're using electric field, which is a vector quantity, and that makes our calculation a little messy, because we have to deal with the directions inside the integral, especially if we're using other coordinate system other than rectangular coordinate system. And so this property of electric field, which is the curl of the electric field, equal to 0, gives us some remedy in dealing with vectors inside the integral. So a vector whose curl is always 0 is equal to a gradient of some scalar. We have learned that from the lectures 1 to 6. And so we define actually the potential to be this. E is just a gradient of some scalar v, where v here is called the scalar potential. Scalar potential. So in this case, we will have your general derivative here is three-dimensional. So in the case where E is just in the r direction, then your ER, or the electric field, will just be equal to negative derivative of V with respect to R, so that should I say this is just R direction. So your dV would just be negative E dot dr. So if you get the integral of this and then the integral of that, it will give you V equal to negative integral of E dot dr. And in general, V could be in general, E could be in different direction. So your dr would have to be generalized into dl. So we define our potential to be this one here. But we have to take note of the limits here. We have to specify such that at some standard reference point, the potential would have to be finite, or in the case of potential at infinity, the we can set the value at infinity to be 0, so that our potential would just be a function of r. So we call the V as the electric potential. It's not potential energy. The electric potential has units of volts, which is equal to Newton meter per coulomb. So if you want to get the potential difference between 2 points A and B, then you have to do this. This is the potential of V minus potential of A, and in basic physics we usually denote this with VAB, which is the potential difference between points A and B. By the way, VBA is equal to, these are equal in magnitude, but the sign is opposite. So this is just, they're just equal, or should I say VAB is equal to negative of VBA. So here you have integral of E dot dl, that's from a reference point to B, minus negative of the integral of E dot dl from a reference point to A. So you can reverse the limit here, so that by reversing the limit you also get a negative sign here, and therefore you can then add the two integral, you can combine them, and then you have VAB would just be equal to this. I mean, this is now the definition between, the definition of the potential between 2 points A and B. So our gradient of potential being equal to the electric field comes from really from the fundamental theorem of gradients here, which is this one here. Now proceeding, we have this now. By the way, a surface in which if you measure the potential is the same at any point in the surface is called an equipotential. By the way, as we will learn later on, the surface of a conductor is an equipotential surface, always an equipotential surface. So when you measure the potential at every point on the conductor surface, it would be the same. So what are the advantages of the potential formulation? First, we dealt with a vector quantity E in our calculation of the of the charge of, like like we do integrals with vectors when we used E, but now we are able to do integrals using a scalar, and this scalar is just the vector potential, the potential V. Sorry for mentioning vector, but the scalar potential V. So we must now be particular of the reference point. So we can always set the potential to be 0 at infinity, because if we have a concentration of charge at some point, we can go away from the charge, and that charge will have no effect at infinity. And so we can set that at infinity the potential is 0. But for the potential difference, you may choose any reference point. It doesn't really affect the potential difference. As you can see from here, you have an arbitrary reference point. So here you can set an arbitrary reference point, and so let's say, of course, this reference point is different from our initial reference point, so that you can actually separate the integral into O prime to 0, and then you have 0 to R, and that will just give you some constant which will be cancelled if you get the potential difference. So this will just be, this was actually VB plus K, and your VA here would be VA plus K, some constant, and that would just cancel, so that you are still measuring the difference at potential difference at 2 points to be equal. Ordinarily, the potential can be set at 0 at infinity. So we can choose a reference point that's where the potential is 0, and this could be at infinity. But this reference point that we choose is only good for some charge concentration at some region, but when the charge distribution is going to infinity as well, then we cannot set V to be 0 at infinity, but rather we can set potential which has some value at some point. Say for example, the value of the potential at x equal to 0 would be some value V sub O. So we can also do that. So like for example, in a uniformly charged plane, the charge distribution extends to infinity in this case, so we can set some value at some point. So but in general, if you have just charge distribution which is at only at some region, then we can set the electric field to be 0 at infinity. The potential also obeys the superposition rule. So just like the force, the electric field, although force and electric field are vectors, the potential also follow the rule of superposition. So the potential at any given point is the sum of the potentials due to all the source charges separately. So we now go to an example. Find the potential inside and outside a spherical shell of radius r, which carries a uniform charge, surface charge, sigma. So let's just put it as sigma. So we set the reference point at infinity. In this case, this is a charge distribution only at a certain region, so we can set our reference point to be at infinity, and at infinity the potential would be 0. So find the potential inside and outside the spherical shell of radius r in this figure here. So the Gauss law says that the electric field coming from a sphere is radial in direction. So here would be, so the direction of the electric field would be here. It's radially, I mean my drawing is not accurate, but you can see a radial direction of electric field. So that means that at any point on the surface of the sphere, the direction of the electric field is perpendicular to that area on the surface. So that is the electric field, and the field inside is 0 because by Gauss law you cannot enclose a charge inside if you draw a Gaussian surface inside the sphere, because the charge resides outside. So if you draw a Gaussian surface outside enclosing the sphere, the sphere with charge, then you can enclose a charge and that would give you an electric field. But inside the sphere, you will have a Gaussian surface there. You will never enclose a charge inside. So the electric field inside that sphere is 0. Outside would be not 0. So for points outside the sphere, you will have this one. So VR is equal to negative integral of 0 to r E dot dl. So E is just negative 1 over 4 pi epsilon sub O. That's the integral from infinity to r. Here we just set our integration variable to be r prime, so we can use r prime in our electric field because our limit is r. So we can set a different variable of integration. So you have the integral of dr prime over r prime square would be just negative 1 over r prime, so that cancels the negative here, so that becomes a positive. And so when you evaluate it at r, it gives you 1 over 4 pi epsilon sub O q over r, and if you evaluate it with infinity, it gives you 0. So the whole thing would be your VR is just equal to 1 over 4 pi epsilon q over r. The potential inside the sphere, which is this small r less than r, we can break the integral into two sections. First is from infinity to r at the surface, and then from the surface r, radius r, to r, where r, the small r, is smaller than the big R. So this one, outside the surface, you have from negative infinity to r, and the electric field here is not 0 outside, and inside you have 0, so everything here would be 0. And so when you get the potential inside, it would be just contributed by this one here. So eventually we have a potential inside, which is a constant, so that the derivative of that constant is 0. So the electric field, which is the derivative of the potential, is 0 inside, but the potential is not 0. So in this case, you have a potential inside which is not 0. This means that when there is a disturbance outside the sphere, what's inside the sphere could detect that disturbance. So if a second uniformly charged shell at radius r prime greater than r, the potential inside r would change even though the field would still be 0. So there will be an added potential if you enclose that sphere with another sphere, charge sphere, so the potential inside would change as well, but it's still constant inside. Any point there would have to be the same potential, but it's not 0. But of course the electric field inside the configuration would be 0. So you have here some problems which you can solve on your free time. Now we go to the Poisson's equation and Laplace's equation. So the electric field can be written as a gradient of a scalar potential, which is given by that. And if this could be written like that, then our differential form of Gauss Law, which is this one, could be rewritten, and of course our curl of E can also be rewritten. So here we have, now we can write, because of this, we will have this as an equation, and that is called the Poisson's equation, where the Laplacian of V is just equal to the negative of rho over epsilon sub O. And of course the curl, this means that this is the curl of E, and therefore you have a gradient here. In general, the curl of a gradient is always 0, and we know this from the first 6 lectures. Now we can solve the potential of a localized charge distribution. So for the potential of a localized charge distribution, it would be easier to get V first. Then when you get V, then you can calculate E by getting the gradient of V. So if we get the gradient of V, we can, in all with all the components of E, we can be derived by from the gradient. Also, the Poisson's equation says that when you have the charge distribution rho, then you can also find the potential. So how about getting V by knowing the charge distribution? In this case, the Poisson's equation must be inverted. So again, beginning with a point charge at the origin and setting the reference point in infinity, the potential of a point charge Q at the origin is given previously by this one, and in general, the potential of a point charge Q is given by this, and R is the distance from the charge to the point R. So in this case, you have in the figure, you have a single charge, which gives you a potential, this one, and then you also have a discrete distribution of charge, and this is a continuous distribution of charge. So you can do different techniques in integration. This one just follows the superposition rule, and this one you have to integrate different dV, the contributions of this charge distribution here. So for a continuous distribution, you can set dq. So say for example, if it's an area distribution, then dq would have to be sigma dA, or for a volume distribution this would be rho d tau, and for a line distribution this would be just lambda dl, your dq. And of course you just use the superposition principle for discrete distribution of charges. So if you look at equation 2.29, you would have an integral which deals with vectors inside the integral here. I mean this one here, this one. But with the potential, you actually don't have a vector inside, so it makes calculation easier. Warning, it is assumed that the reference point is at infinity and the value there is 0. If these formula are applied to artificial problems in which the charge itself extends to infinity, the integral will diverge. Now we'll go to a second example for this lecture. So in this example, we will find the potential of a uniformly charged spherical shell of radius r in this figure. And actually this problem is just the same as the previous one. This example is just the same as the previous example. But we will use now this equation to find the potential instead of using the electric field. So we set the point R on the z-axis to make the problem easier, and use the law of cosines to express r hat in terms of the polar angle theta. So since you have a uniformly charged spherical shell of radius r, this means that your charge is distributed on the surface of the shell. So it's like an surface charge density. So you will be using sigma instead of the rho. So an element of surface area on this sphere is r. Why capital R? Because r is, the dA. The dA is at the surface, and so you have the radius r there. So you have r sine theta hat d theta hat d phi hat. R squared sine theta prime, d theta prime, and d phi prime. So your potential would now look like this. This just a sigma your dq is sigma dA. And so your dA would be this one, and your R would be using cosine law, your R prime, your scripted R would just be equal to square root of R square plus Z square minus 2RZ cosine of theta prime. So that's your scripted R here. So then that would be this one, and you can pull out 4 pi epsilon sub O and transfer it to the other side, and then you will have only with this one. And the integral of concern is only with respect to theta prime, because the d phi prime integral would just be 2 pi for the whole sphere. And then when you integrate that, you will have this one here. So you can set u equals cosine, or you can set u to be for this particular integral. This is this could be easy, because you can set u to be or u square, or maybe just u, or u square maybe, or yeah, just u. You can use to be r square plus z square minus 2rz cosine theta prime, and then you derive it, and you derive both sides. Du would just be equal to some 2rz sine theta prime d theta prime. So it would be easy to integrate. So now you will have the integral to be of this form, and then so this one is given by that. There's a warning here: be very careful in taking the positive root. Yes, because z could be greater than r, and so this one is okay, but this one would have to be always noted, because if z is greater than r, then you have to have if z is greater than r, then r minus z would be negative, and if z is less than r, then that would be okay. So for points outside the sphere, which is z greater than r, you will have r minus z square. Square root of that would be z minus r. And for points inside the sphere where r is greater than z, then this would be the square root. So the potential outside the sphere would be this form, and the potential inside the sphere would be this form, because of the terms here. So as you can see, you have your potential outside goes to infinity, goes to zero at infinity, while inside it remains constant. So these are some problems which you can solve on your free time. Just use the basic principles and the common sense, of course, and the basic principles have been discussed earlier. So for the next lecture, we will be dealing with electrostatic boundary conditions. So that's for the next lecture. So for now, please digest the contents of this particular lecture, and I hope that you have learned something, and see you in the next one.